So what I would like to do this morning during the seminar is go over any questions that you have. I also want to tie in what we've been doing here to solving things graphically, because I think solving graphically is a very useful tool, and every now and then in Math 20-1 and 30-1 we go, oh, by the way, you can solve these equations graphically, and then we move on, and students seem to forget that you can solve equations graphically. It doesn't even matter what kind of equation it is. Let's take a look at these questions, though. When you're solving an absolute value equation, and I'm going to go back even 2 days to when we first learned this on Thursday, the idea is that the absolute value component of the equation, which we can call an absolute value function, can be written in pieces. So, I know we're used to thinking of a function as being y is equal to, but a function of x is just an expression that has x that you can use to calculate values of that function, of that thing. So when you write x minus 5 piecewise, when you write x plus 5 as an absolute value piecewise, even though there's no y, one of the pieces is just x plus 5, and one of the pieces is negative 1 multiplied by x plus 5, and each of these pieces is only valid over a particular domain of values for x. So this even goes back further than Thursday. And what you have to do is determine that domain, or that what I call subdomain, over which each of those expressions takes over for the absolute value. And again, I'm not even talking right now, everybody, about this equals to 10. I'm just talking about taking that function, the absolute value of x plus 5, and splitting it into two pieces. If the absolute value sign is not required, which is the very first expression, just x plus 5, then the argument, which is x plus 5, must be positive, or 0, which means x has to be greater than or equal to negative 5 when you solve this. And that means that the other expression would be x is less than negative 5. So that would be what you would do if I asked you to write the function, the absolute value of x plus 5, in pieces. Now let's get back to reality here. This wasn't just a function, it was an equation that contained an absolute value function. So if the absolute value of x plus 5 is equal to x plus 5 when x is greater than or equal to negative 5, then this equation, and this is what I've been calling equation 1, would be x plus 5 equals 10 whenever x is greater than or equal to negative 5. Be aware, everybody, that when we were doing these, this entire thing here, we weren't doing separately each time. I'm just reminding you that a few days ago we learned how to do that. So that is an equation that you solve. A number line is very useful for understanding what this domain of numbers is representative of. Any number that lies on the number line at negative 5 or to the right of negative 5 would be allowed in that expression. So when you solve this equation, and I'm not going to, well, x equals 5 when you subtract 5 from both sides. I guess I'll write it down. It's not a big deal. All you have to do then is take a look at your domain and see if it fits in the domain. And if it does, it's not an extraneous solution, which means if it does fit in the domain, it's an answer to the problem. Your second equation, which I've always been calling them 1 and 2, is when you take negative 1 multiplied by the argument. That has to equal, in this case, 10. This is only valid for x is less than negative 5. So this is equation 1. And this is equation 2. And your subdomains have to make up all real numbers. You can't have any breaks anywhere in the subdomains. So when you solve this, you have a little bit more work to do. You multiply that -1 through. I would personally move the x to the other side where it becomes positive, and then I have to subtract 10, so I get -15, and we look up there at the subdomain for equation 2. And, you know, I could have just written the subdomain for equation 2 beside equation 2. But is the solution that we get in the subdomain? Yes. Okay, so what did we do Thursday? Well, on Thursday, we looked at solving equations like C and D in question, I believe this is 2, where they are quadratic. And look, the bottom line is if you solve a quadratic equation, you know you can get up to 2 solutions. Just stopping for a second, slowing down, you go back to whatever unit it was. I think it was the last unit, the one before this. When you solve a quadratic equation, you can get 2 solutions. You can also get only 1, or you can get none. But if you think about this, then if you have an absolute value function that has quadratics in it, then you're going to extract 2 equations that will each be quadratic, which means you could potentially get 4 solutions. Now, you may not get 4 solutions because maybe there's only 1 solution to a particular quadratic, or maybe there's no solutions. Or maybe there's 2 solutions, but one of them is extraneous because of the absolute value. You have all kinds of combinations swirling around. Now, the thing that is different here, it's very easy for us to say equation 1 is x squared minus 26 equals 10. And it's very easy for us to say equation 2 is -1 times x squared minus 26 quantity equals 10. But finding the subdomains is different than finding the subdomains for a linear absolute value equation. Because when you take the argument, which I'll highlight, the work we did in finding the subdomain, it's easy. You just take that argument, you say it's greater than or equal to 0, you rearrange for x. If you do the same thing here, so what I'm going to write is not included in my statement of the equation. In fact, I'm going to go to a different page, and you say x squared minus 26 is greater than or equal to 0, and I want to turn that into what x is. You might think, well, if I add 26 to both sides and take plus or minus the square root, I'll get it, but it's not. It's complicated. It's not as simple as that. What you need to do is solve this graphically. And I don't mean solve the equation graphically. I mean you need to look at a picture of the graph of y equals x squared minus 26 to find out where that thing, x squared minus 26, is above or on the x-axis. The solution to this is where x squared minus 26 is on or above the x-axis. Because if it's on the x-axis, then y equals 0. That thing is equal to 0. If it's above, then it's greater than 0. You could certainly use your graphing calculator, but we should know, everybody, and every question's different, but we should know y equals x squared looks like this, so x squared minus 26 looks like this. It's going to have 2 x-intercepts. There is going to be, and let me move this a little bit, there is going to be the following 2 pieces. This one and this one that are on or above the x-axis. So you have to find those two x-intercepts. Well, they're root 26 and negative root 26. If you set this equal to 0 and solve it, you're going to get x equals plus or minus root 26. So this is negative root 26, and this is positive root 26. So what is the subdomain for this equation? It's when x is less than or equal to that part that I've got in green is on negative root 26 and to the left of negative root 26. So x is less than or equal to negative root 26. The part in green that's on the right-hand side is at positive root 26 or to the right. So these are your subdomains. And then it's negative, so that will apply to equation 2 in between those two values. And that's tricky. I understand how tricky and slippery that is conceptually. Because once again, you're trying to determine where y is greater than or equal to 0, but you're expressing that as a statement about x. And that's the weird thing. So here, we would write x is less than or equal to negative root 26, or x is greater than or equal to positive root 26. And then here it would be everything in between. So negative root 26 is less than x, which is less than positive root 26. And I'm not going to worry about solving these equations. I don't want to hand wave it away and say it's not important. It is important, but that's not what we're learning here. We learned how to solve those equations in a different unit. And I want to focus this morning on what we're doing now. So you solve each of these quadratic equations, and then you look at the domains. Just to finish off my review here, kind of painted myself into a corner here. In terms of a number line for equation 1, this represents the domain, and for equation 2, this represents the domain. So we have enough time here to go over a couple of questions if you have any, and then if we still have a couple minutes, I would like to show you how to connect these to the graphs of the functions, which we actually know how to graph them without a calculator, but I'm going to graph them with a calculator to solve these. So does anybody have any questions you would like me to go over? Lynette. Okay, so let's take a look at number 3. So we want to solve this algebraically, and it says using the quadratic formula, which tells me that at least one of the two equations is not factorable, but does have solutions. So one of the equations is x squared minus 2x minus 6 is equal to 4, and one of the equations is negative 1 times x squared minus 2x minus 6 equals 4. This is equation 1 and 2. By the way, if we go back to my explanation here, I would hope that everybody is capable of coming up with these two equations, even if you understand 0 about the subdomains and the inequalities. So if you can't get these subdomains, and some of you will not be able to, that's okay. I mean, there's a whole range of abilities in a math class like this. If you are unable to, you can still solve these, but you don't have a domain to look at to check for extraneous roots. What you would do is just put that number into the original equation and see if it works. Okay. If we were to look at the subdomains here, I'm going to go through this relatively quickly. We're interested in the argument being x squared minus 2x minus 6. And if we imagine that this is a y function, so we can visualize where it's greater than or equal to 0 and where it's negative, this factors into x minus 4, x plus 2, which means that the x-intercepts are 4 and negative 2. And because the argument has a positive x squared, Lynette, the parabola, if we were to imagine it being a graph, opens up, which means that the part that's greater than or equal to 0 is here and to the left and here and to the right. And we could certainly get those features by looking at our graphing calculator. We don't have to do it by factoring. So that means that my subdomain here is x is less than or equal to negative 2 and, or whatever word you want to use, x is greater than or equal to 4. Don't know why I wrote a. And down here it would be anything from negative 2 up to 4, but not including negative 2 and 4. So now we have to solve these. So I'm going to tackle the first equation, which is x squared. I didn't label them up there, but you understand the first one I wrote is 1. I'm going to zero that equation and solve this. And I can do the b squared minus 4ac thing and discover that b squared minus 4ac, maybe a couple of you can help me out here, is 44. So if you could all do me a favor, please, and calculate b squared minus 4ac and just confirm that we get 44. We do, 44 is not a perfect square, so it's not factorable. So in terms of your kind of flow chart of what you do with quadratics, if it's not factorable, probably your best bet is to use the quadratic formula, hence the hint in the question, which means x will be equal to negative b. B is negative 2, so negative b is positive 2. Plus or minus, again, the beautiful thing about this is we've already determined that expression under the square root over 2a. And, you know, there's a lot of cumulative math in this course. You still need to be able to simplify that expression by first figuring out that that root 44 is root 4 root 11 or 2 root 2. We picked on 4. Well, 4 and 11 are the only real factors of 44 other than 2, but I picked on 4 because it's a perfect square. So I can rewrite the solutions to equation 1 as 2 plus or minus 2 root 11 all over 2. I can factor a 2 out of the top so that I have a factor of 2 on the top and the bottom. My solutions to equation 1 are 1 plus or minus root 11. So if I go back and look at my domain here, and I didn't do it as a number line, but I certainly can. That's a visual representation of my domain. We said for this equation that we got x equals 1 plus or minus root 11. Is that correct? Is that what I had? Okay. So I'm pretty sure they're both valid. I know the square root of 11 is 3 point something. If I take 1 plus 3 point something, I'm going to get 4 point something. But you would, you know, you might not know what root 11 is, so you can go 1 plus root 11. You're going to get 4 point something, which is in the domain. Can you tell me what you get to 1 decimal place, Lynette? 4.3? Okay. So 1 plus root 11 is in the domain, and I'm pretty sure if you take 1 minus root 11, it will also be in the domain. It'll be about negative 2.3 probably, I'm guessing. 2.7, I don't know. Okay, so it's definitely in the domain. So both of those that I've highlighted in yellow are correct. Now if we go to the second equation, which has that -1 in front of it, I have -1, this is equation 2. I have -1 times x squared minus 2x minus 6 is equal to 4. Thank you. I expand this out by multiplying that -1 through the trinomial and get -1x squared plus 2x plus 6 equals 4. I'm in the same boat that I was in before. It's a quadratic equation, so I have to zero it. The only difference I think here is that since I have a -x squared, it's probably wiser. We like dealing with positive a's when we solve an equation that's quadratic. It's wiser to move everything to the right side. Just double check that. I move the -x squared over, it becomes positive x squared. I move the 2x over, it becomes -2x. I move the 6 over by subtracting 6 from both sides. That looks good. In keeping line with, even if you know that's not factorable, you're going to have to calculate b squared minus 4ac anyway. So we calculate that, and I think we're going to get 12. Again, I know it's a Monday morning, but can everybody please calculate b squared minus 4ac? You do get 12. A 12 is not a perfect square, so it's not factorable, which means you have to use the quadratic formula. So x equals -b plus or minus the square root of 12 all over 2a. This can be simplified as well, and I'm not simplifying the one that had root 44, and I'm not simplifying this one just for practice. This could be a written response question, in which case you might want your answers as exact values. Kendra, did you have a question? Oh, I thought I saw your hand. A root 12 is root 4 root 3, which is 2 root 3. I think you see what's going to happen here, the same thing that was happening before. A bunch of 2's are going to cancel. So we get x equals 2 plus or minus 2 root 3 over 2. I won't worry about factoring the 2 out. We know that a 2 cancels everywhere because 2 is a factor of the top and the bottom, and you get 1 plus or minus root 3. Now, let me write that up here to be consistent. So we get x for equation 2 equals 1 plus or minus root 3. And then we have to look at the domain. I will put this domain as well as a number line. Here's your -2. Here's your +4. We're talking about this. So we need to decide, is 1 plus root 3 in that domain? Well, root 3 is about 1.7. 1 plus 1.7 is about 2.7. It is in the domain. Is 1 minus root 3 in that domain? I think it's going to be as well. I think you're going to get about -0.7. So we end up with 4 solutions here. And in kind of summarizing things here, because I don't have a lot of time, I want to show you graphically when we resume class this afternoon. Anyway, I hope that helped kind of refresh your memory in terms of what we've been working on. Have a wonderful day, and we'll see you this afternoon.